Hi everyone, Dr. Burns here with our last lesson in Chapter 7, Molecular Geometry, Intermolecular Forces, and Bonding Theories. Today we're going to be talking about valence bond theory, hybridization of atomic orbitals, and hybridization of molecules containing multiple bonds. So we've talked about this a little bit before, but I want to go one step further here in our last lesson and ask the question, how do bonds form? Well, we know that bonds are formed through unpaired valence electrons. Valence electrons are the ones that participate in bonding. This is how we are able to draw Lewis structures. Right, when we're drawing Lewis structures, we're counting up all of our valence electrons and we're putting them around our molecule in order to form the bonds. So we have the example here that we've seen in the past of the formation of the fluorine molecule, F2. We have our two fluorine atoms, okay, they each have one unpaired electron. And what happens is each of those fluorines say, well, I need one more to pair up to 8 and get an octet, so they share them together. And that shared pair of electrons is what forms a covalent bond. We've looked at that in our previous lessons. So, what it looks like in the orbitals are p orbitals because those valence electrons are in p orbitals because fluorine has its valence electrons in the p shell because it's in the p block of our periodic table. So those electrons are in orbitals, the p orbitals. So what's happening is the orbitals are actually what's overlapping in order to form the bond. So we see here in fluorine, this is where we have those lone pairs in these orbitals here, okay? And then we have our unpaired electrons. And what happens is those unpaired electrons are going to overlap through that orbital there. And that's how they form the bond. So we see the bond right here through these two p orbitals. So the theory we're going to look at today is called valence bond theory, and according to valence bond theory, atoms share electrons when their atomic orbitals overlap. A bond forms when single occupied atomic orbitals on two atoms overlap. So single occupied meaning that they have one electron. The two electrons that are shared in the region of the orbital overlap must be of opposite spin. So they have to be like that. The formation of a bond results in a lower potential energy for the system, for the molecule overall. So the electrons would rather be in bonds than unpaired. And that's going to come in handy in our next few sets of slides where we're going to talk about how electrons can rearrange themselves through valence bond theory. So, we've seen the evidence of valence bond theory in many of our examples previously. So here's the HH bond, the single bond between two hydrogen atoms. Okay, hydrogen has one electron in the 1s, and then we have another electron in the 1s. All that we have to do in order to form this bond is say, well, this electron can change its spin. Let me fix my box there. And have a down spin, and then they can come together to form the hydrogen bond right here. So they're overlapping those s orbitals. Remember, our s orbital looks like a sphere, S for sphere. We also have our example again of our f orbitals. So the FF single bond in F2 forms when a singly occupied 2p orbital of the F atoms overlap. So we just looked at that in our very first slide not too long ago. So we see that there's that unpaired electron. When it goes to the other fluorine, we're just going to say that the other electron has opposite spin. They're going to switch their spin in order to pair up, okay? And that is going to be more energetically favorable. The problem comes in when Well, what if there aren't enough unpaired electrons? So here's carbon. Here's the valence electrons in carbon are shown in yellow. Carbon has 2 unpaired electrons, suggesting that it can make 2 bonds. And it says since there's 2 unpaired electrons, it can only make 2 bonds. But we know from our rules of atoms that we've learned in our previous lessons, carbon likes to have 4 bonds. And we've proved that through our Lewis structures. We've shown, for example, CH4 has this Lewis structure where it can form 4 bonds. So if 4 bonds are being formed, that means that there has to be overlap between 4 orbitals. But as carbon as is in our orbital diagram up here, there's only 2 orbitals that can overlap, because the overlap of orbitals can only be if they're singly occupied, if they have 1 electron. So what we actually see carbon do is rearrange all of its valence electrons to maximize how many electrons are unpaired. So let's look at that. So the electrons in carbon's valence shell would prefer to unpair into other orbitals so that they could be paired up through a bond, because the electrons would rather be paired up via a bond rather than being paired up with an electron in its orbitals or being unpaired overall. So one of these s electrons is going to move up into that p orbital, and then we're left with 4 unpaired electrons. I now have 4 unpaired, which equals 4 bonds. 4 bonds that can form, which then allows us to create structures like CH4 and abide by our carbon rule of carbon bonding 4 times. This right here, this changing of the electrons, is the basis of valence bond theory. Okay, so overall, this is called the process of hybridization. And the specific process of moving electrons to higher energy orbitals is called promotion. So we're promoting an electron from a lower orbital, lower energy orbital, to a higher energy orbital. So in carbon, we went from S to P. We could also move things up to the D. We can go S to D. We can also go P to D. We can move electrons around as we need to in order to form bonds based off of their structure. So hybridization itself is the mixing of different types of orbitals in the valence shell to make a new set of hybrid orbitals. So since we're starting to move these electrons around, the orbitals all have to look alike. And we know that an s orbital and a p orbital, they don't look alike. A p orbital and a d orbital, they don't look alike either. So they mix together to make a hybrid orbital. Now there are only 5 types of hybrid orbitals that we need to know. Okay, so it's sp, sp2, sp3, sp3d, and sp3d2. And how those hybrid orbitals are formed is based off of the atomic orbitals of the central atom and how they are forming the bond. So an sp hybridized orbital is made up of an s orbital and a p orbital from the central atom. The electrons that are forming bonds are in an s orbital and a p orbital. And we make 2 hybrid orbitals. So we make 2 sp hybridized orbitals. For sp2, the electrons that are forming bonds are coming from one s orbital and two p orbitals. So what does that look like? Well, if I were to draw my boxes, I would have electrons. I would have an unpaired electron in my s and two unpaired electrons in my p. And they come together to create an sp2, and they make three of those hybrid orbitals. Next up, we have sp3, and hopefully we can start to see the pattern that's going on. sp3 means that we have one s orbital and three p orbitals, so I'd have an extra electron, unpaired electron in my p orbitals. Once I've finished up all three of my p orbitals there, I can't go any higher than that because there's only three orientations of the p orbitals. We then move on to d, so our next hybridization is sp3d. And this just means that my electrons that are forming bonds are coming from an s orbital, three p orbitals, and a d orbital. And I create 5 of those orbitals. Our last type of hybridization is sp3d2. Okay, so that's coming from one s orbital, 3 p orbitals, and 2 d orbitals. And I make 6 of those hybrid orbitals. Now we stop at 6 because that's our maximum number of electron groups we can have around a central atom. Okay, so that then corresponds to our electron domain geometries. So this would correspond to octahedral. Probably write that better. 5 is then trigonal bipyramidal. 4 is tetrahedral. 3 is trigonal planar. And 2 is linear. On our chart that we've looked at in previous lessons where we talked about our different geometries, molecular geometry, electron domain geometry, in that chart there is also a category for hybrid orbitals or hybridization, and those values are given here because these specific hybridizations correspond only to these electron domain geometries. Okay, so whatever the electron domain geometry is, we automatically know the hybridization of that central atom. Now what we're going to explore today is how we hybridize and what that actually means for the molecule overall and the electrons that are being shared. Another tip I'd like to share is that the superscript of these hybrid orbitals tells us how many of each type of orbital were used to create the hybrid orbital itself. So we have S1, P1. I used one S and one P orbital. If we add those up, we then get the number of hybrid orbitals that are formed. Okay, that also tells us our number of electron groups. So the sum of the superscripts is equal to the electron domains. I should say the number of electron domains. So SP has 2 hybrid orbitals, meaning it has 2 electron domains corresponding to a linear electron domain geometry. sp2 has 3 electron domains. 1 plus 2 is 3. That corresponds to trigonal planar. And it's important to note here that lone pairs reside in hybrid orbitals. And we'll look at that more in detail. So we're comparing our hybridization only to our electron domain geometry because lone pairs matter. Electron domain geometry, we take lone pairs into account as well as bonded pairs. In molecular geometry, we only look at the bonds. Okay, so this one, hybridization, number of hybrid orbitals and everything like that directly corresponds to electron domain geometry. Okay, so let's look at our different types of hybridization. So we have sp3 hybridization. So an atom with 4 electron groups around it will have tetrahedral geometry and is made up of 4 electron domains. 4 electron domains corresponds to having sp3 hybridized orbitals on the central atom. Atoms are going to use those hybrid orbitals for all bonds and lone pairs. Okay, so that's what we were just saying before, bonds and lone pairs. So this is specific to electron domain geometry. So if you look at the example here, my carbon has sp3 hybridization because it has 1, 2, 3, 4 electron domains. And my nitrogen also has sp3 hybridization because it has 1, 2, 3 electron domains that are in bonds and a 4th electron domain that is in a lone pair. So both of these central atoms would be tetrahedral, and both would then have sp3 hybrid orbitals around them. So earlier I said that that hybridization is when we mix our orbitals together so that they can overlap. So this image kind of shows exactly what that means. So hybrid orbitals are a mixture in shape of the orbitals used to make them. So let's say we have an sp3 hybrid orbital. Well, we know we're going to make 4 types of 4 orbitals overall, because sp3, 1 plus 3 is 4. Okay, we're going to add up our superscripts there. We're taking an s orbital and our 3 p orbitals here, and essentially what we're doing is we're overlapping them here, and they're making a hybrid orbital. They're mixing together in different ways. And this is what those hybrid orbitals look like. They have kind of one large side and one smaller side. So here's, let me draw a different color. Here's a red version. We have one large side and one smaller side. So they get the 2-lobed character from the p orbitals, and then they get the different sizes of those lobes because of how the s orbitals and the p orbitals are mixing together. And we can see here, if I can draw this a little bit better, we have an orbital here with a short guy out there, and then there's another one back there. It's 3-dimensional, so there's another one right here. So there's 4 orbitals that were formed. And those 4 orbitals are sp3. So that's what the orbital is called. Instead of being an s orbital or a p orbital, it's a hybrid of those, and we call it an sp3 orbital. Okay, so we've shown this before. So here's how we can show that hybridization going on and the promotion of the electrons. So this is just another view of that to show how we can mix these together to create 4 equal energy hybrid orbitals, because the rule of valence bond theory is that forming bonds is more energetically favorable, so the energies are going to change. So here again is carbon, the orbitals of carbon. We see we have 2 electrons in the s and 2 electrons in the p. And what's going to happen is when we hybridize, one of these electrons is going to move up here. They're then going to form these hybrid orbitals at an energy that is about average with these 2, so somewhere in the middle. And they're now having 4 orbitals, those sp3 orbitals, because they're mixing together and forming those hybrid orbitals, but they're now all of the same energy so that they can overlap with other orbitals of similar energies. So let's practice that promotion. So using the images below, place the electrons into the hybridized orbitals. So all of these, so this carbon and this nitrogen, they're all going to form sp3 hybridized atoms. Okay, so we've shown carbon before, and basically what we're doing is we know that carbon is going to form an sp3 hybrid orbital because it can only form 4 bonds. Okay, I only have 4 electrons to work with, so all we have to do is fill in our boxes just like we normally do in our orbital diagrams, following Hund's rule and Pauli exclusion principle and the Aufbau principle, still following those rules. but now we have some extra boxes to work with, so it's going to change how they look. So I have 4 electrons in carbon here. I'm going to show that 1, 2, 3, 4. So I've used up all 4, and they're now all in their hybridized orbitals, all unpaired. So this means that carbon can bond 4 times. If we go on to nitrogen now has 5 electrons that we need to fit into our sp3 hybrid orbitals. So again, we're just going to start putting in our electrons, following all of our rules. We're going to do 1, 2, 3, 4. I have 1 electron left. Since all of my hybrid orbitals have their single electrons in them, we're going to still follow our rules and say, okay, now I will pair up. So my 5th electron is going to pair up in one of those orbitals, one of those hybrid orbitals. Okay, so this hybrid orbital diagram here for nitrogen shows that nitrogen will bond 3 times and have 1 lone pair. The lone pair is right there. So when we draw structures like NH3, we have our 3 bonds, change my color, 1, 2, 3, which correspond to these electrons here that can form bonds. But then we have our lone pairs that are also in that hybrid orbital. Okay, so this is why we say that the hybrid orbitals are for bonding and lone pair electrons. So this also reinforces our rule of nitrogen, that nitrogen prefers to have 3 bonds and 1 lone pair because the hybridization works out that way. Let's look at a few more examples that also follow our rules of specific atoms. So here we have chlorine. If I wanted to make chlorine into an sp3 hybridized atom, well, I have to take its 7 electrons and put them into the hybrid orbitals. So again, we do 1, 2, 3, 4, 5, 6, 7. So whenever I draw chlorine, it always has 3 lone pairs and a bond. The 3 lone pairs are 1, 2, 3, 1, 2, 3, there they are, and our bond is right here. So our hybridization is what's controlling those rules of specific atoms that we've talked about in our previous lectures. Our last example is oxygen. Our rule for oxygen was it likes 2 bonds and 2 lone pairs. Okay, so we have, let's do the example of water. Okay, 2 bonds, 2 lone pairs. Let's take its 6 electrons, 6 valence electrons. Let's put those into hybrid orbitals. We have 1, 2, 3, 4, 5, 6. So those hybrid orbitals, we see our 2 bonds. There's our 2 bonds there. And then we see our 2 lone pairs. So those rules that we had about our individual atoms, nitrogen, carbon, oxygen, fluorine, chlorine, bromine, they were actually there because that's how the hybridization works out for it, but we couldn't say that before because we hadn't learned it yet. So our hybridization now proves those rules to us as to why those specific atoms prefer those specific setups, numbers of bonds and numbers of lone pairs, because the hybridization is what's controlling that. Okay, so now that we have these mixed orbitals, so now that we have these hybridized orbitals, they can now overlap to share electrons and to form bonds. So here we have 2 examples. One is forming CH3. Oops, I need a pen, not a highlighter. CH3. Nope, CH4. There we go. And NH3. There we go. So if we look at our structures that we know about CH3 and NH3, CH4, sorry. There we go. So we have our 4 hybrid orbitals that are sp3 hybridized. Now that they have both s and p character, they can overlap with s orbitals, right? The same orbitals like to overlap with each other. So hybrid orbitals have both s, p, and in the cases of any of the higher hybrid orbitals where they have the d involved, they also have d orbital character, so that they can start to overlap with those types of orbitals. So our sp3 hybridized orbitals can overlap with an s orbital, okay? And that's how they're forming their bonds. The same goes for NH3. Okay, it's just now we're only bonding with 4 hydrogens because our lone pair is up here. Because as we showed through our promotion and how we made those hybrid orbitals, the lone pair of the nitrogen comes from the hybridization and accounting for all of its valence electrons. Okay, so let's practice this. Let's determine the hybridization of each of the molecules below. So the first thing that we're going to want to do is draw our Lewis structures for each of these compounds. And then we're going to look at their central atoms and determine what their hybridization is. And along the way, I'm going to show you a few tricks to make it a little bit easier for you. So what I'm going to do first is draw out the Lewis structures for all of these molecules. I'm not going to spend the time going through all of our steps of Lewis structures as we've learned that previously. So if you need to pause the video and take a second to draw these Lewis structures on your own, feel free. If your Lewis structures don't match mine, then please use your rules to double check that. Okay, so we have BEH2. We have NH2 minus. Remember that minus matters when we're drawing our Lewis structures. So this is going to be like that. Don't forget your bracket with the negative out there. We have PCl5. Okay, and then our last one is ICl4 minus, another ion that we have to account for. I'm going to draw that over here. And again, I'm trying to draw my Lewis structures that are in similar setups to our geometries and how we see it on our geometry chart, just so that it's easier to visualize. Okay, so what we want to do is determine the hybridization of each of these molecules. So we have to look at the central atom, we have to look at its valence electrons, and we have to think about how those electrons would move around into different orbitals in order to change their hybridization. So let's look at beryllium. Beryllium originally has 2s2. That's where its valence electrons are in the 2s orbital. And there's 2 of them. It's in group 2. So in order to unpair these, what we're going to do is we're going to promote one of those electrons into the 2p orbital. So we have our 2s and our 2p. We're going to promote one electron here and one electron there. So our bond is going to be made up of one s orbital and one p orbital. So s1p1. So this hybridization is sp. Now we said before that our hybridizations relate to our electron domain geometries. Okay, so our electron domain geometry for BEH2 is linear. And if we look back to our chart from previously in this lecture, as well as our chart of electron and molecular geometries, we can see that we have a column there for hybridization. For 2 electron domains and a linear electron domain geometry, that corresponds to an sp hybridized orbitals. Okay, so let's look at nitrogen next. Nitrogen has its valence electrons in the 2s and the 2p. So we have 1, 2, 3, 4, 5. When we see an ion and we're looking at hybridization, that extra electron there is going to be accounted for in the central atom. So I'm going to add an extra electron there for my ion. So we have to account for it in our central atom for the hybridization to be correct. So we can't move these any further. I can't move those electrons around anymore. I don't have access to a 2d orbital. There is no 2d orbital, so I can't move those up any further. So in order to form hybrid orbitals, I have to use one s orbital. So I'm going to write that over here, s1. And I need to use 1, 2, 3 p orbitals. So my hybridization is sp3. And we can show that by saying that these orbitals now, there's going to be 4 of them. They go 1, 2, 3, 4, 5, 6. There's an extra electron to account for the ion. So I have 2 places to make bonds and 2 lone pairs, which corresponds to our structure. Now again, to relate this to our geometry, okay, we have 1, 2, 3, 4 electron domains, meaning this is tetrahedral. And if we look on our chart, tetrahedral has 4 electron domains, and that corresponds to sp3 hybridization. We can also, again, do our sum there. We have s1p3 that equals 4. That's 4 electron domains. 4 electron domains is tetrahedral. Okay, so let's use our little trick backwards now and see if we can predict what our hybridization is going to be. So on PCl5, I have 1, 2, 3, 4, 5 electron domains. 5 electron domains is trigonal bipyramidal. If it's trigonal bipyramidal, 5 electron domains. 5 electron domains means it has 5 hybrid orbitals. So remember, our hybrid orbitals are s1, p3, and after p3, that's when we go into the d. So if I do sp3 and then a d, that's 3 plus 1 plus 1, that's 5 electron domains. Those look like eyes. They are not eyes, those are ones. So they sum up to 5 for 5 electron domains. So based off of our electron domains, we would expect this to have sp3d hybridization. Now let's prove that. We have phosphorus. Okay, phosphorus has, similar to nitrogen, we have 3s, 3p, 2 in the s, and 3 in the p. Now, what we can do here, if we remember from expanded octets, row 3 and lower on the periodic table, so row 3, 4, 5, and 6, they can all have expanded octets because they have access to d orbitals. Because we're in the 3 shell, I have a 3d orbital that I can now move my electrons into. So what we're going to do is we're going to say, okay, we can have electrons in the 3s, we can have electrons in the 3p, and we can have electrons in the 3d. I can't do that with nitrogen here. I can't do that with nitrogen, oxygen, or carbon because of the 2. Okay, after 2, we don't have any d orbitals available. We only get d orbitals in the 3, n of 3 or higher. Okay, so this follows our rules of expanded octets. So for phosphorus, I have access to that 3d orbital, so that allows me to have more unpaired electrons. So in total, I have 5 electrons that I'm working with phosphorus. So I'm going to start putting them into my orbitals following my orbital rules. So I have 1, 2, 3, 4, 5. So because I have access to that 3d orbital now, I now have 5 completely unpaired electrons, which means I can create 5 bonds, which is an expanded octet. So this is why that 3d orbital is important, but only from row 3 and lower on the periodic table. Lower meaning further down, not lower in number. Okay, so if I wanted to make bonds, I would be using electrons from one of the s orbitals, so s1. I would be using electrons from 3 of the p orbitals, and I would be using electrons from 1 of the d orbitals. So that corresponds to what we predicted before of having sp3d hybridization. Okay, so this would look like it's not. So 1, 2, 3, 4, 5, that's our sp3d hybrid orbital diagram there. Okay, and for our last example, we have ICl4-. Okay, so let's use our little trick from before. We have 1, 2, 3, 4, 5, 6 electron domains. 6 electron domains is octahedral. Octahedral corresponds to sp3d2. So if we add up all of those superscripts, we get 6, which corresponds to 6 electron domains. Okay, so let's do a little bit more practice. What I want you to do here is draw the Lewis structures for all of these compounds. Yes, you're going to have to determine the names because I do not give them to you here, or you're going to have to determine the structure because I only give you the names here. So draw the Lewis structures and then determine the geometries. Okay, so that should be a little bit of review from our previous lessons, and then bring it together with what we just learned and relating our electron domain geometry to our hybridization, and determine the hybridization of all of these molecules. So pause your video and draw out these Lewis structures and start figuring out their geometries, and feel free to go one step further and predict their hybridization, and then come back to the video to check your work. Okay, I quickly drew out my Lewis structures for these. Again, if your Lewis structures do not match mine, please pause your video and review your Lewis structure rules to make sure you're getting the correct Lewis structure. So we can use our chart now to determine our electron domain geometries and our molecular geometries. So if we look, sulfur tetrafluoride has 5 electron domains. 5 electron domains corresponds to trigonal bipyramidal. Okay, that's the electron domain. Iodine trichloride also has 5 electron domains. That would also be a trigonal bipyramidal Just because they have different numbers of lone pairs does not mean that their electron domain geometry is any different, because a lone pair and a bonded pair are both considered electron domains. Finally, we have dihydrogen monoxide, also known as water. Okay, so we have 4 electron domains on water, so that would be tetrahedral. Now for our molecular geometries, we want to take only just the bonds into account. So when we have 5 electron domains and 4 of those are bonds and 1 is a lone pair, that corresponds to a seesaw structure. When we have 5 electron domains, 2 of which are lone pairs, 3 of which are bonds, that corresponds to a T-shaped structure, which we can see this makes a little T. Okay. And finally, when we have 4 electron domains, 2 are bonds, 2 are lone pairs, that is a bent structure. Okay. So now we're going to relate our electron domain geometries to our hybridization. If we're looking at our chart, our electron geometry chart, we can see that if we have 5 electron domains, that corresponds to a hybridization of sp3d. How can we double check that? Well, we add up our exponents. 1 plus 3 plus 1 is equal to 5. That's 5 electron domains. Because our electron domain geometry is what controls our hybridization, since iodine trichloride also is trigonal bipyramidal, it would also have sp3d hybridization. Okay, so even though they have different numbers of lone pairs and bonds, they still have the same hybridization because the electrons are in the same types of orbitals. Okay, they're just organized differently. Some have more pairs, some don't. And finally, we have tetrahedral. Looking at our chart, tetrahedral 4 electron domains corresponds to sp3 hybridization. So if we add up our exponents, 1 plus 3 is 4 electron domains. Okay, let's continue on. What if we didn't know what our central atom was? Okay, how could we find the number of hybrid orbitals or the type of hybrid orbitals? This is where our electron domain geometry really comes into importance. Okay, so for each of these structures, determine the electron domain geometry, the number of hybrid orbitals, the type of hybrid orbitals, and the molecular geometry. My PowerPoint here has a small typo. This should be a lone pair there. There we go. Okay, so those 2 lone pairs, hopefully it didn't get messed up on the lecture pack, are on that central green atom. Okay, so pause the video and determine or fill out as much of this table as you can. So we can start off by counting our number of electron domains. In our first structure we have 6, in our second structure we have 6, and in our third structure we have 3. So 6 and 6, those correspond to the same electron domain geometry, which is octahedral. And for our last one, 3 electron domains is trigonal planar. Okay, our number of electron domains tells us the number of hybrid orbitals we need, because our hybrid orbitals have to equal how many bonds or lone pairs we have to accommodate. So if we know our number of electron domains, we automatically know our number of hybrid orbitals. if we know our electron domain geometry, then we also know the type of hybrid orbitals that we need. Okay, so 6 for octahedral is sp3d2. Add up those exponents and they equal to 6 for 6 electron domains and 6 hybrid orbitals. The same goes for our second structure here, sp3d2. Okay, the lone pairs versus bonds don't matter. Okay, and our last one is 3 hybrid orbitals or 3 electron domains, which corresponds to sp2. Add up those exponents, you get 1 plus 2 is 3. 3 hybrid orbitals, 3 electron domains. Okay, now we can take our lone pairs into account. Since my first structure here has 5 bonds and 1 lone pair, my molecular geometry becomes square pyramidal. My second structure has no lone pairs, so if there are no lone pairs on the central atom, then the electron domain geometry and the molecular geometry are the same. So the molecular geometry would also be octahedral. The same can be said for our third structure. Since it has no lone pairs, its molecular geometry and electron domain geometry are the same. So this would be trigonal planar. Okay. Now, what happens when we have multiple bonds? We've talked about double bonds and triple bonds and how in structures they are just considered one electron domain. But what does that mean in terms of our valence bond theory and how the orbitals are overlapping and everything like that? So, valence bond theory and hybridization can be used to describe the bonding in molecules containing double and triple bonds. So each carbon has 3 electron domains. So these are, even though we have multiple central atoms, they are mirror images of each other. So each carbon has the same number of electron domains made up of 2 single bonds and 1 double bond. Okay, so this would effectively be sp2 hybridization, right? 1 plus 2 is 3 electron domains, also known as trigonal planar electron domain geometry. Again, we can look at our chart that's given on our ALEKS exams. Okay, it's all there where you have the number of electron domains, you have our geometries, and then we also have our hybridizations listed. So trigonal planar corresponds to sp2 hybridization. Okay, so sp2 would suggest that we have 3 orbitals, each with 1 electron there that are going to be unpaired in order to form bonds. Okay, which makes sense for carbon because it has electrons going in 3 different ways because it has 3 electron domains. The double bond is where things start to get a little tricky. So what we want to do is, again, we want to maximize our unpaired electrons on our carbon by doing our promotion. Okay, so like we were showing before. Okay, so I've moved all of my electrons in carbon. I've moved 1 up to my p orbital, so I've maximized my unpaired electrons. But as I said before, this is sp2 hybridized. So I only need an electron from my s orbitals and 2 of my p orbitals. So those are the only ones that are going to hybridize. But I have this 1 electron left in a p orbital that's unhybridized. So we hybridize the required number of atomic orbitals, 1 for each electron domain on carbon. Okay, so that's 3. 1, 2, 3, sp2. And then we have that 2p electron that's left over. So let's see what that 2p electron does. So the hybridization scheme for the carbon atoms in this molecule, ethylene, C2H4, we get 3 equivalent sp2 hybrid orbitals. Okay, and that explains the 3 bonds around the carbon. Okay, so that has our 3 electron domains around the carbon. But this 1 unhybridized 2p orbital is the reason we have our multiple bond. Okay, so if we think of our electrons in bonds, they're only pairing, each bond is 2 electrons. So I'm going to highlight these. These are going to be my red. So my hybrid electrons are in red. So we have 1, oops, I'm going to localize them on carbon. So 1, 2, 3. I've used up all 3 of my hybridized electrons, okay, to make 3 of those bonds. But what we're missing is that double bond, okay? So this electron here, which I'm going to highlight in blue, luckily we can see that, is this electron there. So it's an unhybridized electron, which allows us to form a double bond. Okay, so the unhybridized electrons is what gives rise to multiple bonds. So if it's unhybridized, that equals multiple bonds. Okay, so we would only see unhybridized orbitals when our Lewis structure has a double bond in it. If there's no double bond, then all of our orbitals are going to be hybridized, because that's going to relate to our electron domain geometry and the proper drawing of our Lewis structures, okay? They all start to affect each other. So when I get down to my double bonds, if I have any unhybridized electrons, that's going to form my multiple bonds. Because I have one unhybridized electron, that's going to give rise to a double bond. Okay, so we have special names for these types of bonds, whether they're being formed from hybrid orbitals or unhybridized orbitals. So a sigma bond, okay, this is a sigma, not just a 0 or something, it's a sigma, Greek letter sigma. A sigma bond forms when sp2 hybrid orbitals on an atom overlap, okay? In a sigma bond, the shared electron density lies directly along the internuclear axis, so the axis that goes directly between 2 atoms, okay? So that's our internuclear axis. And I should make one change here. To be more generalized for our sigma bonds, this should not say sp2, this should just say when hybrid orbitals overlap. Okay, so it could be an sp2, it could be an sp, it could be an sp3, you can even have an sp3d2 that could be considered a sigma bond. Okay, so when hybrid orbitals overlap, that's a sigma bond. Okay, so this is what's going to be on our internuclear axis. Every bond that we see in a molecule includes at least one sigma bond. Okay, so all bonds have a sigma bond. Every single bond is a sigma bond. Single bond meaning one bond. Okay, not every individual bond. Okay, so every single bond, and not a double bond, not a triple bond, is a sigma bond. The ethylene molecule contains 5 sigma bonds. So like I said, every single bond is a sigma bond. Okay, so I like highlighting these rather than describing them by words. So a sigma bond is where we have overlaps. Okay, so we have an overlap here between our C and our H orbitals. We have here with our C and our H. Here again with our other C and our H's, so that's 4. And then every single bond is a sigma bond, meaning that if there's a double bond, one of these is going to be a sigma bond. Okay, so we have sigma, 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 sigma. With a double bond, one of them is sigma, the other one we'll talk about in a second. Okay, so we've got another sigma there. So we have 5 sigma bonds all together in the ethylene molecule. So what we want to talk about next is, well, what's this bond called? What's that considered? Well, that's called a pi bond. Pi bond, that's down here. So the remaining unhybridized p orbital is going to be perpendicular to the plane in which the atoms of the molecule lie. So here's our internuclear axis that we said sigma bonds all form on. Okay, they're all in the same plane. The unhybridized p orbital is perpendicular to that, so 90 degrees. 90 degrees, perpendicular. So here's our p orbitals, okay, that are unhybridized. They each have 1 electron in them. So they're going to form that double bond, okay, by being next to each other. Okay, so the unhybridized p orbitals overlap in a sideways fashion, and they form a pi bond. So a double bond is made up of one sigma bond and one pi bond. So I like to draw this where I have, here's my double bond. I'll put some carbons there, but this applies to any double bond. One of these, and one of these. So we defined red before as a sigma bond. And we define the other one now, that's a pi bond. Okay, so a double bond is made up of one sigma bond because one bond is being formed in our internuclear axis, the definition of a sigma bond, internuclear axis. And the other is a pi bond. Definition of a pi bond is sideways overlap of orbitals, which is right here. Okay, so we have a pi bond and a sigma bond. Now if we move on to triple bonds, well, it's the same concept, it's just now we have one more unhybridized orbitals, unhybridized p orbital. So triple bonds are made up of one sigma bond and two pi bonds, okay, coming from the two unhybridized p orbitals. So if I wanted to make a triple bond, this would be linear, also known as sp hybridization. So I only need two of these orbitals to form my hybrid orbitals, leaving me with two unhybridized p orbitals. Okay, so triple bonds are then made up of a sigma bond, coming from one of those hybrid orbitals, and two pi bonds coming from the two unhybridized p orbitals. So we can draw that again. Here I have carbon, triple bond carbon. Why is this not zooming in? There we go. So we're going to color code these the same way. Red is our sigma bond. Blue is now our pi bonds. So just because it's a triple bond does not mean it's defined any differently. Okay. Yeah, better sigma than that. There we go. So a triple bond is made up of two pi bonds and a sigma bond. So let's practice with that. How many sigma bonds does the following molecule contain? So how many sigma bonds does the molecule contain? Look at this molecule. I'm going to give you some options for answers there. Count up the number of sigma bonds, and then the next question is going to be how many pi bonds does the molecule have? So let's start counting. Let's highlight these. We were doing what? Red is sigma. So every bond that you see is made up of at least one sigma bond. If it's a single bond, it's a sigma bond. So here's a single bond. There's a single bond. Single. So if they're single, they're sigma. Single is sigma. When I have a double bond, I can only define one of those as a sigma bond. So if we count those up, we have 1, 2, 3, 4, 5, 6, 7, 8 sigma bonds. 8 sigma bonds. For pi bonds, when we were highlighting those as blue, pi bonds only come about in double or triple bonds. So since I have a double bond, one of those was sigma, therefore the other bond in the double bond is a pi bond. So I only have one pi bond in this molecule. Okay, so we're just counting up bonds. Okay, let's try another one. How many pi electrons are found in the amino acid aspartic acid? So I want to acknowledge pi electrons. So each bond has 2 electrons. No matter if it's sigma or pi, it still has 2 electrons in it. Okay, so how many pi electrons are in this amino acid? So pause your video, take a look at this amino acid, count the number of pi bonds, and then determine the number of pi electrons. So this molecule has two double bonds. Okay, so we have a double bond here and a double bond there. Okay, so if each double bond is made up of a sigma bond and a pi bond, well, one of these is a pi, one of those is a pi, so I have two pi bonds. But I asked for pi electrons, so we got to be careful to see what the problem is asking. So if there's two pi bonds, each bond has two electrons, so there are 4 pi electrons, right? Because each of these has 1, 2 electrons in them. Okay, the other question is how many sigma bonds does the molecule have and how many sigma electrons, because those are different terms, sigma bond and sigma electron. Okay, so let's count up all of our single bonds. If it's a single bond, it is a sigma bond. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I then have a sigma bond in my double bond, sigma bond in my other double bond. So that's a total of 15 sigma bonds. Each bond has 2 electrons, so that would be 30 sigma electrons. Okay. Let's keep practicing. Determine the number of sigma and pi bonds in the following molecules. So pause your video, count up your sigma and pi bonds in these molecules. I'm going to keep going with my highlighting where sigma is red. So every single bond is a sigma bond. So we have a single bond. So that's 1, 2, 3, 4, 5 single bonds. And then we have a double bond where one of those bonds is a sigma and the other bond is a pi. So for sigma, we have 1, 2, 3, 4, 5, 6 bonds, and for pi we only have 1 bond. Okay, in our next example we have a couple triple bonds, so we got to be careful there. So let's first go through with our sigma. So we have a single. Our double bond in the middle here, only one of those is a sigma, and in each of our triple bonds, one of those is a sigma as well. So I'm going to do the middle one. So those are all sigmas. So for sigma, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, 9 bonds are sigma. And for pi, we now go through with blue. We know our double bond has a sigma bond or a pi bond. And then our triple bonds have 2 pi bonds in them. So we have a pi and a pi, a pi and a pi, a pi and a pi, pi and a pi. So in total, that's 1, 2, 3, 4, 5, 6, 7, 8, 9 pi bonds as well. Okay. Okay, in our last practice problem here, below is a structure with multiple central atoms. Use it to answer the questions below. How many sigma bonds are in the molecule? How many pi bonds are in the molecule? And how many lone pairs of electrons are present in this molecule? Okay, so pause your video, go through this molecule, start labeling up your sigma and your pi bonds. Okay, whether you're using slashes, I've had some students who have gone through and counted this way where they use slashes, others who use highlighting. however way you can keep track of these multiple sigma and pi bonds, go for it, okay? So take a second, pause your video, determine the number of sigma, pi bonds, and the number of lone pairs. Okay, let's go through with our highlighting again. I'm going to go through my sigma first. We're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. So it's 33 sigma bonds. For pi, we count up all of our double bonds. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 pi bonds. Okay, and then for lone pairs, I guess I'll highlight those as well. I'll use green. I have 1, 2, 3, 4, 5, 6. I have 6 lone pairs. Okay, so that finishes up our lesson of our last lesson of chapter 7. So before you move on to your next chapter, please make sure that you're completing your ALEKS homework and your ALEKS exam and preparing best you can for that exam.